The game objects in our scene can be arranged in a hierarchy. That is, a game object can have a parent, and so that means that also game objects can have multiple children. So here, for example, I'm going to take my cube and make it a child of my sphere just by dragging it on top of it. Now this indentation is implying that the cube is a child of the sphere. We can give the sphere other children, like I can take my manager here and make it a child of sphere, or I can make manager a child of cube, and now we have a hierarchy going 3 levels deep, where cube is manager's parent, sphere is its grandparent, or we also say that cube and sphere are its ancestors, and manager is their descendant. But I'm going to put that back, make it its own independent object. And the significance of this hierarchy is that, well, one, you may just want to arrange your game objects in a hierarchy for the sake of organizational purposes. Like, say, you might just create some empty game object which you want to use as effectively a container, a parent for a bunch of other objects which need to logically be grouped together. That's something you might do for organizational purposes. But the other significance of this hierarchy is that when an object is positioned in space, first its own transform is applied, but then its parent's transform is applied to it as well. So here the cube, when it's positioned in space, it's not only its own transform being applied to position it, but then also after that, the sphere's transform. And if, say, here I'll make the directional light a child of cube, now when directional light is positioned in space, it's not just its own transform, but then the cube transform and then the sphere transform in that order. So we go up the chain when the transforms are applied. So let me just put that directional light back. And the significance of this then, well, in the simple case, here now, because sphere is a parent of the cube, if we move the sphere around, the cube is moving around with it. Because when the cube is positioned, we're not actually modifying cube's transform here. Let's actually see that in action. Let's open up another inspector tab, bring that down here, drag it up, and then we're going to lock this so it stays on being the sphere. And then we're going to select the cube and lock this inspector so we always see the cube. Okay, and as we can see here, when I move the sphere, notice only the X position of the sphere is changing. The transform of the cube is remaining untouched. But the cube does move along with the sphere effectively, because when this cube is positioned in world space, its own transform is applied, and then the sphere's transform is applied. In some cases, though, this produces some strange effects. The classic example is if I were to apply a so-called non-uniform scaling to a parent, like here I'm going to make this y3, so x and z are still 1 for scale, but then we're applying y3. And if the child object has some rotation on it, here I'll just rotate in a few directions to make it even more obvious. Yeah, so you may be able to tell right now that our cube is no longer a cube. It has been skewed. And that's happening because, well, that just always happens whenever you rotate an object and then scale it after rotation, you're going to get weird distortion to the vertices. And so that's why we no longer have a cube here. And probably this is not what we had in mind. It's not what we expected. So generally the guideline then is to avoid non-uniformly scaling your parent objects. And if you want to get what may be the expected behavior, like you may assume, well, okay, so the sphere itself is just along its own local y-axis, it's growing 3 times. And you want the same thing to happen to the cube. That can be arranged. There are various solutions to that problem. But by default, this is how the transformations work. I believe to get the behavior you're probably expecting, where this cube doesn't get skewed, it just grows along its own local y-axis. I think to get that behavior, Unity would have to apply the scale of cube's ancestors before it applies its own local rotation. And that would work. That would fix the skew problem. But for efficiency reasons, that would be more expensive because of the nature of how data is laid out in memory. So the engine doesn't want to do that. So anyway, its default behavior does create some aberrant cases like that, which perhaps are not expected and which you're going to have to try and avoid. Also understand that some weird things can happen, that after positioning objects and removing them as children or adding them as children, Unity will try and update the transforms when you do this so that it preserves what you see. But because of the skew effect, you're not always going to get perfect results. So you're going to take the cube and make it its own independent object. And yeah, so now it's removed the skew. But it's preserved the position. And you may have noticed, here I'll just undo that. Notice that our transform of the cube is being modified. Its values have to change so it can stay in place, because right now, as a child of sphere, to achieve this position in space, it requires applying the transform of the sphere. But then when we make it independent, these values need to be modified. We need to effectively take these values of the sphere transform and use them to update the values of the cube transform. And Unity is doing that automatically. Here, let me put the cube back as a child of sphere. And notice up here, there's this toggle between pivot and center. That affects if we select an object that has children. When the pivot mode is active, when you do transformations on the sphere, it's as if we're doing that transformation relative to the center of the sphere. And when I do rotations, we're rotating around the pivot point of the sphere itself. But, let me put that back and go into center mode. And now we're rotating, the center here is the center point between the pivot of the sphere and its children. So now it's sort of in between the sphere and the cube. And now when I apply a rotation, it's doing so around that point. It's repositioning the objects accordingly. Look at the transform. It's not necessarily just updating a single value in the transform. That's normally what was happening when we were moving objects around. But now Unity is doing the extra math to figure out, well, to get this effective position and rotation in space, what does the transform then have to look like? So it's doing some extra work. And also up here we have the local versus global toggle. Local meaning that we're transforming around the axes local to the object or group of objects. Here, let me make that pivot again to make it a bit more clear. Whereas global would be the global XYZ axis. So now we'd be rotating around the global XYZ. This would be around the local XYZ. And again, when I do these transformations, notice that it's not just one rotation value that's being updated, it's all three. Unity is doing the extra math to figure out what the transform needs to look like to get this apparent position. So anyway, getting used to these controls can be a bit tricky. You'll need to play around with them. The core concept to keep in mind, though, is that what's really ultimately going on is that your objects are really positioned by the transforms, starting with its own transform, and then by applying the transforms of its parents. That is the ultimate source of most confusing behavior you'll see when you try and position objects in Unity. Rotations in particular tend to be the part that makes things confusing. We'll play around with rotations quite a bit later when we talk about quaternions and manipulating rotations in our code. So we still have the same setup here. We have cube as a child of sphere, and our manager has a MyScript component where the cube object is mapped to the cube field and the sphere object is mapped to the sphere field. And looking at the code, what we want to do is in our awake method where we're doing our scaffolding work of like hooking up objects together, perhaps we want to, from an object, get at its parent or its children. So first here, we're logging out from the cube, we're getting its parent and logging its name, and from the sphere, we're getting its parent and logging the name of that. But notice that cube and sphere, which are game objects, they don't directly have a parent property. Instead, we have to get it through the transform. That's a bit strange, but remember, again, internally, transforms and their game objects are really one and the same thing. And for whatever reason, maybe there's an efficiency reason, they decided that you can only access parents and children through the transforms rather than directly through the game objects. Now let's see this in action. Come here, play. And we get printed out cube parent is sphere. That's what we expected. But we also get a null reference exception. And that we get because here we're accessing the name of the parent of the sphere, but the sphere has no parent. So this is giving us back null, and we try and access the name of that, and you can't do that. That gets us a null reference exception. And now down here we have this loop that's going through all the children of the sphere, and it does so by accessing the count of the number of children, again through the transform of the sphere, not directly through the sphere itself. And then we use getChild on the transform and an index value to get back the actual child, except again, be clear, we're getting back a transform and not the game object itself. Yet, if we want to access the name of the game object, we can do so directly through the transform because it has a name property, but that's really just the same as if we were to write t.gameObject.name. This would be the same effect, but just for convenience, we can directly get at the name. And so this is printing out the name of the sphere's child. And now to see this in action, well, I need to comment this out so we don't get that null reference exception. Come back here. I'm going to duplicate the cube. So the sphere has multiple children. Now I'm going to play the game. And we see cube parent is sphere still, yes, but then sphere child, cube 1, sphere child, cube 2, and cube 3. Another thing we may want to do in code is change these child-parent relationships. Like say here on sphere, on its transform, we're calling detached children. That takes all of its children and makes them independent of the parent so that they themselves are now root objects. But then here we're taking the transform of our cube and setting its parent to be the sphere. And again, the way the API exposes this is it's not really the game objects that have the parent-child relationships, it's their transforms. So we're passing in a transform of the sphere, not the sphere itself. So now with this code, if we print out all the children of the sphere, it should actually only have one child now, even though in our scene we have 4. So let's see that in action. So yeah, the cube parent is sphere, but then the sphere only has the one child, the first cube. And notice that here in the hierarchy window, we see the live state of the hierarchy. We detached all the cubes from the sphere and then reattached the cube to the sphere, and we're seeing that state reflected here. But be clear, these changes are just transitory while the game plays. When I stop the game, our scene is again as we defined it in the editor. So all the cubes are children of the sphere, at least when the scene loads, and then in our code, we're detaching them all and then reattaching just the first cube as a child of sphere. Now, if we just want to detach one child from its parent, we shouldn't use detached children because that detaches all of them. Instead, the child we want to remove, we set its parent to null, and that will detach it. So now cube will have no parent. I'm going to get rid of this line so we don't get a null reference exception there. And go back and play. And as you can see, so just the one cube got detached and the remaining cubes remain as children. And in fact, there's also a parent property which we can set, and we can also set that to null, and this would do the same thing. So this code is equivalent. Another little convenience that strangely is not mentioned in the documentation. If you look at the definition of the transform class, you'll see it's an IEnumerable. It's something that can be iterated, and it's actually then something we can iterate over in a for each. And when we do so, what we're getting back is the children transforms. So this here is basically the equivalent of what we did when we looped through the children of the sphere. And we're just printing out all the names of the children of the sphere. So this is just a more compact way to loop through all the children of our sphere rather than writing this code here. Annoyingly, they don't mention this in the documentation. Okay, so we can walk up and down our hierarchy of objects and access their transforms, but often in code we'll want to get at the other components that make up our game objects. And we can do that with a few methods, including getComponent, which is a generic method where you specify the type. There's also a non-generic version of this, but the generic is the most convenient to use because having specified the type here, that determines what kind of component we're accessing, and it also tells the compiler that what this call returns is of that type. So we want to store our mesh render component, for example, in a mesh renderer reference, and so it's just most convenient to use this generic form. So now, from the sphere, we're getting its mesh render component, storing an M. And again, a transform and its game object are really kind of the same thing internally. So the getComponent and similar methods are also accessible through the transform, and they do the same thing. So this line of code is doing exactly the same thing the previous one did. It's getting the mesh render component of the sphere and assigning it to M. So now we have our component. What can we do with it? Well, that depends on the kind of component, and we'll get into the details of the various component types later. For now, though, there is one thing which all behavior components share in common. Remember that many of the component types inherit from behavior, which in turn inherits from the component type. And what behaviors add on top of the base component type is they have an enabled property. And as you would expect, when the enabled property is true, that component is active and does its normal business every frame. But when we set the enabled property to false, then we're effectively disabling that component. It does not have its usual effects. Its business does not get performed every frame until we re-enable it. So in this case, if we're disabling the mesh render component of our sphere, that should have the effect of making the sphere no longer render. Logically, it's still there. The object still exists. It's just its rendering is not getting done. So the significance of this flag depends upon what kind of component we're talking about. In this case, it's just a matter of whether something gets rendered. And then down here, in addition to getComponent, there's getComponents, plural, in children. And we specify a component type. And this will return an array of mesh renderers, including the mesh renderer of the object itself, the sphere itself, but then also all the mesh renders of its children as well. And I believe this only goes one level deep. So if our children had their own children, it wouldn't look for the mesh renders in those children, just the immediate children of the sphere itself. Anyway, so having gotten back this array, we're not going to do anything with it except just print out its length. Similarly, we have a getComponents in parent method. This time we're getting the transform component, but it's going to include the transform of the cube itself and its parent, which is going to be the sphere. So we should expect this length here to be 2. So let's see this code in action. Come over here, hit play. And num renderers is 5 because we're getting back a mesh render for the sphere and all of its 4 children. That's 5. And then num transforms is 2 because the transform array will include the cube transform, the first cube's transform, and the sphere's transform. Actually, there's sort of a strange asymmetry in the API here, where if I make here sphere a child of manager, now the cube has 2 ancestors. It has its direct parent sphere, but then also its grandparent manager. And if we run the code again, num transforms is 3. because get components in parent isn't just looking at the immediate parent, it's going up through all the ancestors. So we're going to get back 3 transforms here. But again, get components in children doesn't behave like that. Get components in children just goes 1 level deep. It just finds the components in the immediate children. It doesn't traverse through all the descendants. I'm not sure why there's that asymmetry. It's probably some sort of efficiency thing, or maybe they decided that that's the behavior most commonly needed. But of course, we don't really need these methods anyway. If we ever really need to get at the components we want, we could just traverse the tree of objects and collect the components we need into our own array.